Hi everyone, welcome back to Introductory Physics, day 18, I think. So today we are going to be doing some examples dealing with conservation of momentum. So remember yesterday when we were talking about conservation of momentum, the whole idea is that momentum, the total amount stays the same throughout the whole problem. So momentum can change from one object to another, um, but the total amount is going to stay the same the whole time. And that's a really key thing to keep in mind as we go through these examples today. We'll also be talking about different kinds of collisions and how those different kinds of collisions will affect the way that we approach these problems. But first of all, I wanted to go through a problem-solving strategy for you guys for how to solve these conservation of momentum examples. So first step, identify. We're going to decide whether or not momentum is conserved. Now, in almost all of the cases that we'll do together, maybe all of them, momentum will be conserved, but that's only true if the vector sum of the external forces is 0. So if there's no net external force that's acting on our system, then momentum is conserved and we can use conservation of momentum. If that's not true, then we can't use conservation of momentum and we have to approach the problem a different way. So to set up the problem, we're going to define a coordinate system just like we've been doing in the past, show it in a sketch, and show which direction is positive for each axis. So again, usually we'll choose up, right, north, east, forward, those directions to be positive, and then west, south, down, backwards, left, etc. to be negative. But there will be some times where we'll have collisions not in the x-axis direction. And so usually it's easiest to just rotate our coordinates so that the x-axis is in the direction of one of the initial velocities of the object. And then we're going to use an inertial frame of reference. So again, we're not dealing with anything like relativity or anything like that at the moment. We're going to treat each object as a particle and draw a before and after sketch. So before and after the collision, showing what the velocities are doing, what the motion of each object is like, and if we know any other details, things like masses or angles or quantity, like velocity numbers, we'll include those in our drawing as well. And then we'll figure out which variables we don't know. So we'll give those variables that we don't know a letter, usually, just so that we can still incorporate them into our equations. And the book recommends that you use subscript 1 for things that are before the collision and subscript 2 for things that are after the collision. Sometimes you might see people use I and F for initial and final, but I'm going to keep it for the most part with 1 and 2 because that's what the textbook recommends that you do. That's what the textbook examples will do. And most professors use this textbook. So just for consistency's sake, that's what we're going to end up doing. And then using letters to label your objects instead of numbers for your objects. So like ball A and ball B as opposed to ball 1 and ball 2. So again, that's just the book's preference, but we'll keep going with that since that's the book's preference. And then lastly, to set up, we're going to identify the target variables, so what we're actually looking for in the problem. There will be more unknowns than we actually need to find, so we got to figure out which one of those unknown variables we're actually interested in knowing about. And there's a question here, would more advanced physics classes go away from treating each object as a particle? Yes, absolutely they will. Things like physical mechanics, analytical mechanics, those sorts of classes, the more advanced physics classes, you don't just think about things as a particle or as a box or some easy calculated shape like that. But again, those are the more advanced classes, so we won't do that in this class. And wouldn't treating an object as a particle require quantum mechanics? Not that kind. That's not the kind of particle I mean here. So by particle, we just mean like if I could condense myself from this like awkward cylindrical shape into just like a point. So when I draw it in a diagram, I'm just representing myself as a point as opposed to drawing my actual body every single time. That's what we mean as a particle. We mean my whole self is acting as one object. And I'm not thinking about my arms like flailing as I fly through the air or anything like that. So that's what we mean by a particle. We don't mean like a subatomic particle, like think of me as an electron. It's more like think of me as a tiny little ball with no flaily little bits coming out the sides. Does that make sense? Okay. Yeah, so that's what we mean by a particle. It's just a simple shape with no flaily bits. Okay. So when we actually execute the problem and go through and solve it, we will write an equation in symbols. So we want to equate the total initial x component of momentum with the total final x component of momentum. And then we'll do the same setup with the y direction if we have a y component to momentum, and same thing with the z direction if we have a z component to our momentum. So we will never mix our directions in the same equation. Okay, just like with kinematic equations and projectile motion and forces, pretty much every vector thing that we've done in the past, we always want to think about x and y separately. So we'll set up separate equations for those. Make sure you pay attention to your signs. Both velocity and momentum are vectors, so the direction matters, right? We're going to use positive and negative according to the coordinate system that we establish. But again, that will depend on the problem, but really we use our standard up, right, etc. as positive and down and left as negative. And then, of course, we're going to solve our equations to find that particular quantity that we're interested in. So keep in mind, you might have to convert into components or from components into a magnitude and direction, depending on what your question is asking you to do. And sometimes in these problems, energy conservation can also help us when we get stuck at a certain point dealing with momentum. In some cases, some kinds of collision, energy is also conserved. So we can use conservation of energy ideas like we've been doing last week, and that will help us solve some of these problems. But in other cases, energy is not conserved, so we won't be able to use conservation of energy if energy is not conserved. And we'll go through what times you can and what times you can't use energy conservation in a little bit. And then lastly, as always, we want to evaluate our answer and see if it makes sense. So check and make sure the sign or the direction of your final answer is logical. Yes. All right, let's go ahead and solve a problem. Example 5, recoil of a rifle. A marksman holds a rifle of mass 3 kilograms loosely in his hands so as to let it recoil freely when fired. He fires a bullet of mass 5 grams horizontally with a velocity relative to the ground of 300 meters per second. What is the recoil velocity of the rifle? So are we all set up and ready to go for this problem? Can we just plug numbers into an equation? No, right? Probably if I'm asking that question, probably the answer is no. We're not all ready to go. What do we need to do first? Because of the mass, right? The mass of the bullet is in the unit grams, and the mass of the rifle is in kilograms. Which one do we want for for these kinds of problems. Kilograms, yeah, of course. We pretty much always want to use kilograms as opposed to grams. So we'll need to make sure that when we are using the mass of the bullet, that we convert this into kilograms before we just plug it into an equation. Okie dokie. So here is a picture of our scenario before and after. So this wouldn't necessarily be considered a collision. Remember, because collision is when two or more objects hit each other, but recoil is when two or more objects separate from each other. So as the title of this example suggests, this is a recoil example. So we're starting with the two as like one object, and then after this this event, they separate, and now we're dealing with two objects. Initially, both the rifle and the bullet are at rest. They are not moving with respect to the ground. So our initial total momentum in the x direction is 0. And then, of course, according to conservation of momentum, our initial momentum is the same as our final momentum. The total value is the same. So P1 equals P2. And we're just concerned with the x direction here. We're not really paying attention to the bullet falling down at all. We're just looking at the x direction because that's what we have been asked to do in the problem, right? The recoil velocity in the x direction of the rifle. So our total momentum in the x direction is going to be 0 because if it's 0 before the separation, it'll be 0 after the separation. And if we remember from yesterday, momentum is the real MVP. So momentum for any particular object is the mass of that object times its velocity. So the mass of the bullet times the velocity of the bullet plus the mass of the rifle times the velocity of the rifle. That is our total momentum. When we take that equation and we rearrange it to solve for the velocity of our rifle, we get negative mass of the bullet over mass of the rifle times the velocity of the bullet. So when we plug those things in, remembering to convert our mass of the bullet to kilograms first, we get a velocity of negative 0.5 meters per second. So this velocity, if this were real life, you would feel that rifle hitting into your shoulder at that velocity, and it would not be pleasant to do that repeatedly. So a better practice, I've never actually fired a rifle before, but I know this from video games and TV shows and stuff, that the better practice when you're firing a rifle is to brace it against your shoulder, because then that increases the mass that you're dealing with at the end. Instead of just the mass of the rifle, it would be the mass of you plus the rifle. And so the velocity at the end would be a lot smaller for the rifle plus you. So keep that in mind, I guess, if you ever shoot a rifle, brace it against your shoulder because of momentum. Okay. So next question about this scenario. What are the final momentum and kinetic energy of the bullet and of the rifle? So for the bullet, momentum, again, is mass times velocity. So our mass of the bullet is 0.005 kilograms. We take 5 grams divided by 1,000 to go from grams to kilograms. And then its velocity is 300 meters per second. So its momentum is 1.5 kilogram meters per second. Its kinetic energy, we remember from last week, as 1/2 mv squared. So 1/2 times 0.005 times 300 squared gives us a kinetic energy of 225 joules. We basically repeat this process for the rifle. since we just found the final velocity of the rifle to be negative 0.5 meters per second, and we get a momentum of negative 1.5 kilogram meters per second, which that should make sense to us because if the total momentum is conserved, and it has to be zero in this case because it was zero initially, it has to be zero finally. That means that the momentum of the bullet and the momentum of the rifle are equal but opposite directions. So the bullet is going to be firing to the right in this picture, and the rifle is going to be going to the left. So we get that negative number there. But when we look at the energy here, the kinetic energy for the rifle, we can see a huge difference in their energies. The kinetic energy for the rifle is 0.375 joules. That's not very much energy at all, especially compared to the 225 joules that we got from the bullet calculation. So they end up with the same momentum magnitude, opposite directions, right? But not the same energies. Okay, so yes, that's that example. Do you guys have any questions about example number 5, recoil of a rifle? Okay, so not seeing any questions come in, which is great. If you have questions, of course, type them in the chat and I will answer them to the best of my ability. So when we're thinking about collisions now, the last example was a recoil, so that was different than a collision. Remember, collision is when things are hitting each other, recoil is when things are separating from each other. So shifting our focus now to collisions, things hitting each other. A collision includes any strong interaction between objects that lasts a relatively short time. So this would be things like car accidents, billiard balls or like pool balls hitting each other. It could be neutrons in a nuclear reactor. It could be a meteorite hitting the ground. Any kind of strong interaction, strong hitting between objects is a collision. And usually the forces between these objects are much larger than any external forces. So things like friction or gravity, those are considered external forces. And like when we think about a car crash, for example, right, two cars colliding with each other, the collision, the force between the cars is much greater than the force of friction on the tires or anything like that. And so we just ignore those external forces and treat it as an isolated system. I mean, there are cases where external forces are significant, but then we're not really dealing with conservation of momentum anymore. So that would be a different approach that you'd have to take for these problems. So our different types of collisions, first of all, we have elastic collisions. So this is where the objects bounce off of each other. So things, the billiard balls, for example, we have the two balls and they bounce off each other. They don't like stick together or anything like that. That would be an elastic collision. And so if we have a perfectly elastic collision, then momentum is conserved, but also kinetic energy is conserved, because in an elastic collision, all of the forces between objects are conservative forces. And if you remember conservative forces from last week when we talked about energy and work, when all of our forces are conservative, that means that potential energy can turn into kinetic energy and back, and we don't lose energy to anything like heat or friction or what have you. So in this type of collision, both momentum and kinetic energy are conserved, which is very helpful. If we are dealing with an inelastic collision, which is when objects bounce but not as much. Um, so, like when you're dealing with a car accident and your car hits another car and the bumpers end up being dented, some of that energy is lost in that collision and cannot be recovered as kinetic energy again. So in that case of the car accident, energy, well, the force did work to kind of cave in those bumpers, and they'll stay caved in. They won't give that energy back. So that would be an example of an inelastic collision. And in those cases, momentum is conserved, but not energy. Energy is not conserved in this case. It's all good. Welcome. I'm glad you made it. Car accidents can result in a lot worse than dented bumpers. Absolutely. That would be the case about perfectly inelastic collisions where the objects actually stick together. So we'll do an example of this in just a minute where the cars become like entangled with each other and there's just this mass wreckage that like the cars don't separate anymore after that. So in that case, momentum is still conserved, but some to all of your energy is lost in those cases. And since those objects are sticking together, the final velocity of both objects are equal to each other because they move as one object at the end of the collision. So yeah, Casey, that's a great example. Planets forming, right? We take all of these chunks of rock and such in space and we collide them together and they stick together and accumulate more and more. That would be an inelastic or a perfectly inelastic collision. Accretion, yes. I like that example. That's a good one. Okay, so we have these three different types that we will be dealing with, and we'll do examples of each type. Yeah, we will today. We'll have an example of all three. For now, though, remember, for all of these types of collisions, momentum is always conserved, even if kinetic energy is not conserved, because we're not dealing with any significant external forces. So we can always conserve momentum, even if we can't conserve energy for now. All right, example 6, car crash. A 600 kilogram smart car is going east at 30 meters per second, and it hits a 9,000 kilogram semi truck going west at 20 meters per second. The two stick together and have the same final velocity. So what type of collision is this? Perfectly inelastic. Good. Yeah, this is perfectly inelastic because they are sticking together. Woohoo! I mean, not woohoo. That's like a terrible thing. Okay, anyway. So we want to know what that final velocity is in this collision. Okay, so here's our little smart car traveling east. Here is our semi truck traveling west. And we know conservation of momentum means that the total momentum is conserved the whole time. So our initial momentum is the same value as our final momentum. Okay, so initially we have the momentum of the car and the momentum of the truck. And then at the end, we have the momentum of the car plus the truck moving together as one object. So momentum, remember the MVP, so mass of the car times its initial velocity, plus the mass of the truck times its initial velocity, and that equals the total mass of them put together times their final velocity. So when we plug in what we know, our mass of the car is 600 kilograms, The velocity of the car is positive 30 meters per second because it's traveling east. The mass of the truck is 9,000 kilograms, and the velocity of the truck is negative 20 meters per second because it's traveling west. And our total mass is 600 kilograms plus 9,000 kilograms, and then we're looking for that final velocity of both of them together. So when we number crunch, negative 162,000 kilogram meters per second equals 9,600 times our velocity. And our velocity then ends up being negative 16.9 meters per second, or 16.9 meters per second west. Both of those are totally acceptable answers. In the first one, that negative just implies that the direction is west. And then in the second one, we're explicitly stating it. But both of them are totally acceptable ways to say that. I mean, I would like to think that I would not drive past a horrendous car crash and be like, oh my gosh, look at that inelastic collision. Because those car crashes are really unfortunate. But yes. Okay. So next question about this. If the collision took place over 0.5 seconds, how much did each accelerate or decelerate? Remember, we don't really say decelerate in physics, but in real life we do, so I'm putting it in there. All right. For the smart car, the acceleration, we can always calculate it to be the change in velocity over the change in time. So this car's change in velocity, it ended up with a velocity of negative 16.9 meters per second minus its initial velocity of positive 30 meters per second in that 0.5 second time interval. So it has an acceleration of negative 93.8 meters per second squared. That is significant. When we compare this to the semi-truck, which we calculate it the same way, but using the truck's initial velocity of negative 20 meters per second, the truck has an acceleration of 6.2 meters per second. So there's a significant difference there in the magnitudes of these objects. So this is what an inelastic, perfectly inelastic collision in this case would look like. These two objects they're not coming apart, right? They are merged together into one object at the end, which, is of course very unfortunate. So that's why when we design cars, we design them with what's called a crumple zone at the front, so that we can try to avoid this type of scenario. Okay, next example, a rugby collision. Two rugby players, Alfred and Bruce, collide head-on. Alfred has a mass of 70 kilograms and Bruce has a mass of 80 kilograms. Just before the collision, Alfred was moving north at 5 meters per second, while Bruce is moving south at 6 meters per second. The players bounce off each other just a bit, such that after the collision, Alfred is now moving south at 1 meter per second. What is Bruce's speed after the collision? Thanks, Marco. I'm glad you caught the reference. Okay, so here is our picture of this. I've actually never watched a game of rugby before, but I'm sure this particular example would be quite entertaining to watch. So here's Alfred, right? He's traveling north at 5 meters per second. Here's Bruce traveling south at 6 meters per second. So this is our before picture. And after, we know that Alfred is moving south at 1 meter per second. And we're not really sure what's going on with Bruce after this collision, what his motion is like. So we just kind of plopped him into the picture there, but we don't really know. So let's find out. Again, conservation of momentum is in play here. So initial momentum equals final momentum. So initially, both of our objects, both of our people are moving. So they both have an initial momentum. And at the end, both of them, we think, are moving. Again, we don't really know what's happening with Bruce. So we're just going to put his momentum into there and see what's going on with him. So momentum, remember, is mass times velocity. So we get mass times velocity of Bruce plus mass times velocity of Alfred equals mass times velocity final of Bruce and mass times final velocity of Alfred. When we plug in our numbers that we're given, Bruce has a mass of 80 kilograms and an initial velocity of -6 meters per second. Alfred has a mass of 70 kilograms and an initial velocity of +5 meters per second. And then he has a final velocity of -1 meter per second. So we're solving for VB2 here in this example. After we plug in our numbers, we get -130 equals -70 plus 80 times velocity. We can simplify that a little bit more and a little bit more until we get our velocity for Bruce is -0.75 meters per second or 0.75 meters per second south. Either of those is acceptable. So think about what that means for this collision, right? This means that Bruce obviously wins in this collision because he ends up forcing Alfred to totally change his direction and move backwards. But Bruce continues to like plow forwards, well, forwards for him, southwards, not through Alfred because you can't really plow through a person, but he pushes him back and is still moving southward himself at the end of this. So I Bruce wins, I guess, in this this particular collision. But you can see there that his velocity has very greatly changed after this collision, right? He started moving at 6 meters per second south and ended up moving at 0.75 meters per second south. So that is a significant change, but he's still going in the same direction. Yeah, exactly. Nothing like a friendly game of rugby between you and your 80-year-old butler. Yeah, no big deal. I'm sure Alfred's up for it. Okay, any questions about this example? Okay, so what type of collision is this? Do we know? Hmm. Well, in this case, we would not have a perfectly inelastic collision because the two objects are not moving at the same velocity at the end of it. They're not actually sticking together. Alfred bounces off, remember, with a velocity of -1 meter per second. So he kind of like bounces off and moves away, like falls away from Bruce a little bit faster than Bruce keeps moving south. So it's not actually a perfectly inelastic collision, but we can't really tell if it's a elastic collision or an inelastic collision unless we actually calculate the energy and see whether or not the kinetic energy is conserved. Now, I don't have an actual slide going through that, but that would be the way that we would have to determine whether or not it's elastic or inelastic. Okay, and our next example is clearly going to be an elastic collision, so like a perfectly elastic one where they bounce off of each other, which means energy will also be conserved here. Kinetic energy will also be conserved. So in this case, two billiard balls of equal mass strike each other. Before the collision, one ball had a velocity of 3 meters per second east, and the other was at rest. Find the final velocity of the two billiard balls. So remember, since this is an elastic collision, they won't be joined together at the end of it. So we'll have to solve for two separate velocities for their final velocities. We had a question here about inelastic collisions versus perfectly inelastic collisions. So remember, in a perfectly inelastic collision, our two objects stick together. And so sum to all of the kinetic energy is lost in those kinds of collisions. But when we're dealing with just an inelastic collision, not perfectly inelastic, the two objects might bounce off of each other a little bit, and still lose some of that kinetic energy, but they're not actually stuck together as one thing at the end. Is there a special term for imperfect inelastic collisions? The special term is inelastic collision. But you might also see people say imperfect elastic, but I would say that's less likely. Usually people will specify perfectly elastic and perfectly inelastic, and then that somewhere in between is just called inelastic. Okay, good. Glad I answered your question. Okay, so here is our scenario. We have ball A moving to the right, east, at 3 meters per second. And ball B is initially at rest, so it has a velocity of 0 meters per second. Okay, so I put in bold and underlined some of the really important things in the scenario that you'll want to take note of as you go through this example. First of all, they are equal mass, which will greatly simplify the math for us, as you'll see in just a couple minutes. And then again, ball A has a velocity of 3 meters per second east, and ball B is initially at rest. So those are the important things that we'll take note of. Now, just like before, conservation of momentum means that our total momentum initially equals our total momentum finally. So our total momentum is the momentum of B plus the momentum of A, and that's true initially and finally. So momentum, again, is mass times velocity, but we should notice that the velocity initially of ball B is 0. So initially, it doesn't really contribute to the momentum of this example. Now, we don't know what the final velocity of ball A is going to be unless you've taken physics before or done this in real life. So we're still going to leave all of the rest of it in our scenario there and kind of mathematically prove what's going to happen. So that means that mass times velocity of ball A initially equals mass times velocity of ball B plus mass times velocity of ball A finally. But since they have equal mass, like we see in the scenario, all of those masses can cancel out because there's mass in every single one of the terms and those masses are all equal. So we'll just take them out of the equation completely. And we didn't even need to know how much the mass of the ball was. Just the fact that they're equal to each other is enough information for us to be able to do that. So now we can plug in our initial velocity of ball A, which is 3 meters per second, and we get this equation. We can't really do anything further with this equation because we don't know what either of the final velocities are. So for the moment, we're kind of stuck here. Except we're not, because this is an elastic collision, meaning kinetic energy is also conserved in this situation. So now we can look at conservation of energy, where our initial energy equals our final energy. And so we're just dealing with kinetic energy here because it's not changing height, so there's no gravitational potential energy to deal with. There are no springs, so there's no spring potential energy to deal with. We just have kinetic energy. So our total initial energy is kinetic energy of ball A plus kinetic energy of ball B. And then same deal for our final energy. It's A kinetic energy plus B kinetic energy. Of course, ball B is not moving at first, so it has no kinetic energy. Kinetic energy is 1/2 mv squared, like we learned about last week. And we have a 1/2 in each of those terms. We also have a mass in each of those terms. And remember, the masses of ball A and ball B are equal, so we can cross those out. And so this is the equation that we're left with. Our initial velocity for ball A squared, which would end up being 9, equals our final velocity for A squared plus our final velocity for B squared. Okay, but we still don't have our final velocity for ball A or final velocity for ball B. So at this point, we're kind of stuck with our energy approach. So here's what we know from our two different approaches. From momentum, conservation of momentum, we know that 3 equals VB plus VA. And from our conservation of energy, we know that 9 equals VA squared plus VB squared. Now, algebra is kind of tricky to solve in these kinds of problems. I will go through it in the next example, but sometimes it's a lot faster and simpler to just try some numbers and see how it goes. So let's do a couple of guesses. Let's say if we think the final velocity for ball A is 1 meter per second, that would mean the velocity for ball B has to be 2 meters per second, right? Because 1 plus 2 equals 3. So when we plug those guesses into our energy equation result, we would get 1 squared plus 2 squared, which gives us 5. And 9 does not equal 5. So we know that those two values for our velocities don't work. Well, let's try something else. Like what if these two balls just kind of share the momentum equally afterwards, and they end up with a final velocity of 1.5 meters per second each. Well, when we plug that into our energy result, 1.5 squared plus 1.5 squared is 4.5. So that's even worse. That's even farther away from 9. So those don't work. Okay, so let's try another guess. What if our velocity for object A is 0 and all of that momentum transferred into our second ball, or ball B, so it ended up with a final velocity of 3 meters per second. That works for our momentum equation, right? 3 equals 0 plus 3, totally valid. And it also works for our energy equation. 0 squared plus 3 squared equals 9, which 9 equals 9. That's good. Hey. So that gives us our only possible solution, really, for this scenario. The final velocity of ball A is 0 meters per second, and the final velocity of ball B is 3 meters per second. So what's happening in our collision here is that all of the momentum from ball A transfers to ball B, and initially ball B was stopped, but afterwards ball A is kind of stopped right there where the collision happened. If you've ever played pool before, you might have seen that happen in your game, which means that you had a perfectly elastic collision and both momentum and kinetic energy were conserved. Yay! So now next time you play pool, you can think of that. You're welcome. So a question here: is there anything beyond the scope of this class that determines which collision scenario plays out? So you mean whether or not it's a elastic versus inelastic versus perfectly inelastic? Yes, there are things beyond the scope of this class that determine that. Things like how those external forces interact with our objects. But that's definitely beyond the scope of this class because we only have a week and a half left together. So You might learn about it more in your actual Physics 1 lecture class, or they might just wait to do examples like that until later, like physical mechanics, that sort of thing. I know, there's only so much we can do in 6 weeks, so we do what we can. I know, I enjoy these sessions together too. This gives me a lot of energy teaching you guys. I like it. Okay, so now we're going to look at an example where our two balls do not have an equal mass, and we'll see how that affects this scenario. So, I mean, I don't know why you would have billiard balls of unequal mass, but let's just say somebody's cheating. Okay, so two billiard balls of unequal mass this time strike each other. Before the collision, one ball has a velocity of 2 meters per second east, and the other was at rest. Find the final velocity of these two billiard balls. So this is still going to be an elastic collision because the balls are still perfectly bouncing off of each other. They're not getting tangled together. We're not playing pool with like balls of Play-Doh or something like that. They'll still bounce off of each other. So it's still elastic, even though they have different masses. So that means both momentum and energy are conserved again. So this time, here's ball A, which has 3 times the mass. And I just picked 3 for fun. It didn't specify in the example, in the scenario, but we're specifying now. Okay, and it's moving east at a velocity of 2 meters per second. Ball B is still at rest, and it has a mass of 1. So we have a mass of 3 and a mass of 1 relative to each other. So that would be like, here's ball A, and here's ball B. Like that. They're hitting each other. What's going to happen? Let's find out. Okay, still momentum is conserved, so our total initial momentum equals total final momentum. Same deal as before. Our initial momentum is the momentum of ball B plus the momentum of ball A, and the final momentum is momentum of ball B plus momentum of ball A. Momentum is, of course, mass times velocity. This is all the same as the previous example. Initially, ball B is at rest still, so velocity is 0, meaning its momentum is 0. So that term goes away, which is very helpful for our math. And so when we simplify that equation, we get the mass of A plus the initial velocity of A equals mass of B plus final velocity of B. Sorry, mass of B times final velocity of B plus mass of A times the final velocity of A. So many variables going on, I tell you. But we know that the mass of A is 3 times the mass of B. Again, we don't know like exactly is this 3 kilograms and 1 kilogram. But from the picture there, we know that the mass of A is 3 times larger than the mass of B. So we'll plug that in for the mass of A. 3 times mass times velocity of A equals mass times velocity of B plus 3 times mass times velocity of A final. All right. So now that we have everything in terms of mass or mass of ball B, we can cancel out those masses. We couldn't do that before because we didn't have the ratio of that, like 3 to 1 in our equation until this particular step. Okay, but now our equation, it's 3 times the initial velocity of A, which is 2. So 3 times 2 is 6, equals velocity of B final plus velocity of 3 times velocity of A final. Again, we're kind of stuck here at the moment because we don't know either of the final velocities. So, like we did last time, let's look at conservation of energy. Remember, initial energy is equal to final energy when energy is conserved. And again, we're just dealing with kinetic energy here, no change in height or springs to deal with. So initial kinetic energy equals final kinetic energy. Ball B is not moving, so it does not have initial kinetic energy. Kinetic energy is 1/2 mv squared, so we'll plug that in. Like last time, we see that there's a 1/2 term in each of those equations. We're not going to cancel out the masses just yet again because we don't have that ratio of masses in our equation yet, that 3:1. So that's our next step to do, right? Plug in mass A equals 3m and mass of B equals m. So we'll plug those in. And now we have m in each term, so those m's can go away. So our equation is then 3 times initial velocity of A squared equals 12, because remember the initial velocity of A is 2. So 2 squared is 4, so 3 times 4 is 12. And that equals 3 times our final velocity of A squared plus our final velocity of B squared. Now we're stuck with energy, so let's look at what we know. Okay, so from momentum, we know that 6 equals 3 VA final plus VB final. And then from our energy approach, we know that 12 equals 3 VA final squared plus VB final squared. So in this case, we're going to go through all of the messy algebra steps just so you can see how to do it instead of just like taking random guesses and plugging them in. Which, I mean, it's still a valid approach, but we'll do it this way, the algebra way this time. So we're going to solve that first equation, the momentum approach equation, for the velocity of B final. And that ends up being 6 minus 3 times our final velocity of A. We'll take that result and plug it into our energy approach equation. So 12 equals 3 VA final squared plus, plug in our result for VB final, and then square that. So when we square what's in the parentheses, we get 3 VA final squared plus 36 minus 36 VA final plus 9 VA final squared. And then we can combine our VA final squared terms. And we get 36 minus 36 VA final plus 12 VA final squared. Okay, so that was all just simplifying that equation. We can simplify it even farther though, because 12 is a factor of 36. So we get 1 equals 3 minus 3 VA final plus VA final squared. And then when we subtract 1 from both sides, we get 0 equals VA final squared minus 3 VA final minus 2. Okay. Is it just me or is there a typo in there? Did I math wrong? I think I mathed wrong. Pretty sure I mathed wrong. I'm pretty sure this is supposed to be a +2. Yes, okay. Something just didn't seem right in my head. I'll fix that before I upload these slides. But for now, we'll just roll through the rest of this example as it is, and then I'll fix it when I upload it. Why did I square it when I plugged it in? Because over here, VB final is squared. And so we got a result for VB final, but now VB final has to be squared. And so that squares that whole term there. Does that make sense, Marco? This, I don't know if you guys called it the FOIL method in when you took Algebra 1 in school. But if you want me to write out how we square this term in the parentheses, I can do that when I post these notes to Canvas. I can show you that intermediate step if you need me to. Okay. Anywho, let's keep rolling, even with the typo. Sorry, my bad. Okay, so that's our result. So this is set up and in a quadratic equation approach. So if you guys remember the quadratic equation, it's the opposite of b plus or minus the square root of b squared minus 4ac over 2a. So when we plug in our things, remember the coefficient of the squared term is what we call a. The coefficient of the not squared term is what we call b, and the coefficient of the constant is what we call c. So when we plug those into our quadratic equation, we get the opposite of b, which is positive 3, plus or minus b squared, so negative 3 squared is 9, minus 4 times a, the coefficient of this is 1, times c, which I have corrected here, so that's good, which is 2, and then times, divided by 2 times our coefficient of the squared thing, which is 1. Okay, so when we simplify and do that math, we get 3 plus or minus the square root of 1, which gives us 2 different answers, right? Because we have the plus or the minus, so we get 2 different answers. So we could end up with an answer of 4 over 2. 3 plus the square root of 1 is 4 over 2. So that would be a velocity of 2 meters per second for A, which would then mean B has a velocity of 0. Or if we do 3 minus the square root of 1, that would be 2 over 2, which is 1 meter per second. And then that would mean that the velocity of B is 3 meters per second. So a question here from Marco, why did you square when you plug in? Wait, so for 3VA2 squared is squaring twice. Let me go back. This is a slide you're asking about, Marco? So in this term, okay, good question. Yeah, the 2 next to the A stands for final. So the reason why I'm using 1 for initial and 2 for final is because that's how the textbook does it. You could use I for initial and F for final if that makes more sense to you. That makes more sense to me, but for the sake of consistency with the textbook, which is the textbook that you'll be using in Physics 1, I left it with this notation where the subscript 2 means final. So it's just the 3 times the final velocity of A squared. So we're not squaring it twice. Does that answer your question? Okay, good. Yeah, I don't know why the book prefers it that way. I definitely don't, but you use your own notation. So if I and F makes more sense for initial and final, just do that. As long as you can keep it straight in your head and don't get it confused with the other things, it's fine. Use whatever notation makes the most sense to you. Okay, so how do we know in this case which set of answers is correct? Well, let's just think about what's actually happening here, right? Initially, ball A is moving at 2 meters per second, and ball B is at rest. So with that first set of answers, if the final velocity of ball A is still 2 meters per second, that means no collision actually happened at all, and ball A just rolled right past ball B. Um, but we know that that's not what happened because it says in the scenario that they strike each other. So there has to be some kind of collision happening between these two balls. So that means that our second set of answers is the one that is correct. And even though ball A hits ball B, it still ends up moving forward, but it kind of shoots ball B out faster at 3 meters per second. And then it just keeps going at 1 meter per second as well. So both of those balls end up going to the east after this collision because both velocities are positive um, in this example. Algebra, there's a lot of it here. So do you guys have any other questions about this example? If the question is, how did we figure out what the velocity of ball B is? That is from this equation right here, our result from momentum, right? 6 equals 3BA plus BB. So if VA is 2, then 3 times 2 is 6, velocity of B would be 0. When I upload these notes to Canvas, I'll go ahead and I'll put that equation up here at the top too, just so you can reference it easier. But any other questions about this example? Momentum examples can get pretty, I don't want to say pretty crazy pretty quick, but they can get pretty lengthy pretty quick. And especially if you have more than one object, more than two objects in a collision, then it's just, it's hard to keep track of everything that's happening, which is why it's so important to use those subscripts. So, you know, labeling your objects with A, B, C, etc., however many you have, um, and keeping track of everything as clearly as you can is really, really important in momentum examples like these. Okay. Well, I'm not seeing any other questions about this example in particular. So do you guys have any questions about any of the examples that we've done today? We will be doing a couple more examples tomorrow. So what happens when we have collisions on angles, not just in like our X direction? We'll do some of those examples. We'll do examples of explosions tomorrow. We'll do examples of more than two objects in one of these. Can we do some shopping cart collisions? Potentially, yeah. I'll try to think of some good ones. Okay, yeah, so we have some more examples in momentum that we'll do tomorrow. And then that will kind of wrap up our talk about chapter 8 before we move into rotational motion. But if you guys don't have any other questions, comments, concerns about the material for today, then you guys are free to go. I know it's 15 minutes early, woohoo! But you guys are welcome to go, and I hope you have a beautiful day. I'll see you guys tomorrow.